from the Laplace transform perspective, our attempt would be to use gamma function in order to find one of the things that becomes very obvious for you to do is integration by parts. And how would you choose integration by parts? After your +2, obviously you may want to take up engineering. And do you realize what are the challenges? It's a matter of observation that many students in engineering struggle with mathematics. And it is attributed to the gaps in calculus and linear algebra, because these are two concepts that are fundamental to every engineering application in mathematics. So here comes a great course that fills all your gaps and prepares you for the challenge of engineering mathematics. So please go ahead, espouse this course and get yourselves prepared for the challenge of engineering mathematics. Now let's try and introduce a very important function called gamma function. Be it quantum mechanics, be it statistics, be it fluid mechanics, this concept is going to be very useful. Now let's try and look at what exactly I'm talking about and then relate that to several incidental applications also. So it's going to be a very interesting discussion, so please watch out for every nuance of the discussion because it's going to be very useful. And of course, from the Laplace transform perspective, our attempt would be to use gamma function in order to find the Laplace transform of 1 by root t, which is a discontinuous function. So therefore, we also argue that whatever conditions that are stipulated for existence of Laplace transform are just sufficient conditions and not necessary conditions. So that's very important, because it's commonsensical to note at t is equal to 0, this is not defined as it tends to infinity. And you can see that gamma function is plotted over here, and you can see that the 0 of gamma function tends to plus infinity, and the negative integers, if you input to gamma function, they don't exist, because you can see they all go to infinities. So that's very important. Now, how do we actually understand all this and then utilize that for Laplace transform, and also look at some important observation? In fact, the Gauss also did not like the gamma function. He introduced one more function, but we found that in higher engineering applications, gamma function is more useful than the one introduced by the Gauss. So now let's we'll also look at the Gaussian distribution. We are going to exploit that in this derivation, but now let's look at what exactly I'm talking about. Now you know the factorial of 5, or if I ask what is factorial of n, you can easily tell us n being an integer, right? Because 5 factorial is nothing but 5 into 4 into 3 into 2 into 1, that's 120, right? But if you press if you Google what is the factorial of half, you still get a value. If I say what is the factorial of half, so 0.5, you still get a value. How did you get to that value? All that's going to be investigated. And so this is one generalization, or you can say expansion of the concept of the factorial theorem or factorial idea that we have got. Now let's try and represent the gamma function in detail and understand all the nuances. So the gamma function is indicated by the Greek letter gamma. So people also use this for gamma. Okay, in thermodynamics you would confront this as gamma. So one is capital gamma, one is small gamma. So it is like you have small omega, capital omega. So it is always better that you are familiar with these symbolisms, very important. So now if I say n plus 1, then how you are going to define? You are going to define in the following way: 0 to infinity, 0 to infinity. And if I choose the variable t power n, and then e power minus t. e power minus t. And if I define gamma of n, then what happens? It's going to be 0 to infinity. It's going to be t n minus 1 e, of course, dt I will have to write. So if you don't integrate, it makes no sense. So this is the definition of the gamma function for a number en. Since we are able to find the gamma for both positive, negative numbers and also for fractions, we are going to see how exactly that's going to be done. So this is the gamma function. So the first thing is we will have to apply this to the Laplace transform, right? In order to find the Laplace transform of 1 by root t. We'll do it in steps. So this is the definition of gamma function. So whatever number comes over here, 1 less to the power of t appears here and multiplied by e power minus t. It is same like the Laplace transform, except that it's going to be s is equal to 1. S is equal to 1 here, and then integrated from 0 to infinity. And at one point, what we do is we'll reduce this to an area under the bell curve. You can see that if I assume my mean in the bell curve to be 0, okay, mean is 0, then the area, if I integrate from 0 to infinity, okay, so that will give the 1/2 of area of the bell curve. Okay, we'll discuss all that, but let's now first establish a very, very important idea, that if you're talking about n plus 1, then that is equal to n into the gamma function n. So this we'll have to establish to begin with. Now once we establish this, then other things easily follow. So let's start with this particular idea. So what we said, you have the gamma function, you have n plus 1, and the definition of the gamma function is given by integral t power n e power minus t dt 0 to infinity. So how would I actually simplify this? How would I get to gamma n? One of the things that becomes very, very obvious for you to do is integration by parts. And how would you choose integration by parts? This as the first function to be integrated, this as the second function, because otherwise t power n, if you integrate, the function keeps growing, so you will be handicapped. So therefore, whenever you are integrating by parts, choose the exponential function for first to integrate, then multiply by t power n. If I choose e power minus t as first function, the second function is kept as it is. Integrate the first function, you get e power minus t by minus 1, and then put the limits 0 to infinity. Hope you are quite familiar with integration by parts. If you aren't, please visit our prerequisite module. So now this is going to be minus. Since you observe here, when I integrate e power minus t, and then I am taking inside the integral sign for the next term, and there is a minus here, so it's going to be plus. And then t power n is going to be differentiated, so that's going to be n into t power n minus 1. So e power minus t by minus 1 I have taken, so minus of minus has become plus here. Okay, so plus here. Remember that why plus comes, because if you looked at the standard formula, it is minus whatever you have integrated, the first function that comes inside, and the second function must be differentiated. But since we got minus 1 here, that into the minus 1 becomes plus 1, plus here. So this dt and 0 to infinity. And you can clearly see that we have been discussing that whenever you have e power minus t and top limit is infinity, this has to go to 0. And of course the lower limit would ensure that t is 0, so this has to go to 0, right? So now what is this? Can you go back and see what is this? This is gamma n. This is gamma n. That is the integral I am talking about, but there is one extra. So therefore, can I write this n plus 1 is nothing but n into n. This is the formula that we are going to exploit very, very significantly as we travel through. So let me recollect. So it is very important that a beginner becomes familiar with this representation. It looks slightly complex but easy to remember. Whatever number comes, n plus 1 comes here, here it is 1 less. Here it is 1 less, and e power minus t, just like your Fourier Laplace transform, but only thing is t has a coefficient minus 1 instead of s. Just like Laplace transform, if you put s is equal to 1 here, it becomes e power minus t, and f of t is replaced by t power whatever number you have, 1 less. So this is the definition of gamma, and I also have the definition of gamma n, because the moment I reduce n plus 1 to n, I am reducing the power also by 1. Remember that? And therefore this is my definition. Now how would I correlate these two? I started with this, started applying integration by parts, and when I applied integration by parts, I chose e power minus t as first function, integrate that, multiply by the second function, apply the limits, and then there is a minus 1 here, so therefore it is not going to be minus whatever you have integrated inside the integral sign, and then differentiation of t power n. It's not just that, but minus 1 also, so that makes it plus here. And when you differentiate t power n, it becomes t power n minus 1 into n, and then e power minus t, because that is what you got on integrating e power minus t. So this goes to 0, because when you put infinity, t is equal to infinity, it is e power minus infinity, which is 0. And then when you put 0, the lower limit, 0, t goes to 0. So this entire term goes to 0. And what you are left with is n into this integral is nothing but the definition of gamma n. So therefore, we have achieved a very important result. Gamma of n plus 1 is equal to n into gamma of n. Clear? So we will make use of this result as we move along. So this is an important result. So please remember, you should never forget. This is going to be very, very useful as we move along. Now let's use the gamma definition, the area under the bell curve, that is the Gaussian curve, and then let's calculate the Laplace transform of 1 by root t. Let's go there, and also we'll use this particular theorem to calculate the Laplace transform of several standard functions, which either have t power minus 3 by 2, t power plus 3 by 2, or whatever. So let's continue. Well, engineering and math are absolutely inseparable. We interventions day in and day out try our level best to make math as simple as possible and also of great practical value to every aspiring engineer. Do you want us to reach the masses? Please like us, share and subscribe. Do not forget to turn on the bell icon.